30 years. He also co-founded the International Panel on Fissile Materials and co-chaired it during its first 9 years. From 1983 to 1990, Professor von Hippel worked with President Gorbachev's advisor, Yevgeny Velikov, to develop several successful initiatives for ending nuclear testing, ending plutonium and highly enriched uranium production for use in weapons, and eliminating excess weapons materials. He's advised US administrations and Congress on nuclear security issues since the Carter administration. And 1993 to 94, Frank served as Assistant Director for National Security in the White House Office of Science and Technology Policy. And he helped to develop US-Russian cooperative initiatives on nuclear threat reduction. So we're very lucky to have Frank here with us today, especially coming all the way from Princeton. As you can see, the subject of Frank's seminar is the saga, the dream reactor, the plutonium breeder. Before you start, Frank, I'll let the audience know that if you have questions for Frank, he welcomes them during the seminar as well as after, but rather than interrupting him, if you wouldn't mind posting them to the chat, I'll try to draw Frank's attention to the question at a time that seems good to interrupt. So Frank, the floor is yours.
Thanks so much, John. And thanks for inviting me, and thanks for people turning up. It's a beautiful spring day up here. I imagine it is down there as well. This is the story of the breeder reactor, and I'm going to just skip this list of slides and go down to the first slide, which features Leo Szilard, who invented the breeder reactor. He's very interesting character. In 1933, Rutherford, the high priest of nuclear physics at the time, was interviewed and said that there was no way to increase the rate of energy release by radioactivity. And Szilard invented and actually patented the neutron chain reaction, but without knowing about the fission of U-235. When the war started, or was about to start in Europe, he immigrated to the United States. Then after he heard of fission, he realized that was what he'd been looking for. And he verified that U-235 releases fast neutrons by bombarding it with slow neutrons with an alpha beryllium. He borrowed a gram or rented a gram of radium, I think, for a week from somebody for the alphas. He then started to think about how you could have a chain reaction and invented the graphite moderated reactor. This was a key thing because in Germany they had rejected graphite, because they didn't understand the small boron impurities in the graphite could make it impossible. But Szilard knew enough chemistry that he figured that out and got very pure graphite. And then he moved with Fermi, from Columbia, where they both were, to Chicago, and with Wigner, they designed and built or had others build the so-called pile, the first chain reacting, the first critical facility. Then he started worrying about what they were doing, and especially after Germany was defeated, was very much against the US being the first to use a nuclear weapon. And he tried inside, the project was still secret, to persuade the government not to do that, unsuccessfully. The picture there is, I think, from a reenactment of the discussion that Szilard had with Einstein, where Szilard drafted the letter to Roosevelt. I've got 3 volumes of his collected work. He's a fascinating fascinating guy. So anyway, he at the end, in 1945, before the end of the war, the job at Chicago for the Manhattan Project having been completed, he started thinking about nuclear power and invented the sodium-cooled, liquid sodium-cooled breeder reactor. And the reason that he did so was the perception was that uranium was very scarce. The graphite reactors that they built to produce plutonium for weapons during World War II exploited only the 7/10 of natural uranium that's U-230, chain reacting U-235. I found a talk that he gave in 1947 where he estimated that we could only have get enough uranium to annually to support, the equivalent of about 2 gigawatts of nuclear powers, and they obviously wanted much more. And then he realized that if you fueled the reactor with plutonium and had enough neutrons coming out of the fission chain, extra neutrons coming out of the fission chain reaction, that you could produce more plutonium from U-238 than you were fissioning. And you could get, you could basically, and then I do a little back of the envelope calculation at the bottom of this slide, where I show that the 3 grams of uranium-238 in a ton of average crustal rock, if fissioned, would produce, about almost 10 times as much heat as the combustion of 1 ton of hard coal. So the breeder would basically turn even the Earth's crust to super coal. And obviously, if we went that route, the humanity's energy needs would be solved for millennia. And there's this famous quote from Fermi: "The country which first develops a breeder reactor will have a great competitive advantage in atomic energy." And that I found that quote being quoted by the people who are trying to build a breeder reactor, a demonstration breeder reactor in India. Well, in order to get enough extra neutrons, Szilard concluded that you would need to go to you need to have a fast fission chain reaction, closer to what you have in a bomb. And I just show in this slide that in fact the number of neutrons you get out of a plutonium fission goes up with energy when you get up to around 1 MeV. And so Szilard realized that graphite or water slows down neutrons, and he needed and that's because especially in the case of water, that a collision of a neutron with a proton nucleus and hydrogen, you can bring the neutron to a dead stop in one collision, just like with the billiard ball. And so he thought it would be necessary to have a coolant for a breeder reactor, which would not not slow down the neutrons so much. And I show at the bottom here of this slide the neutron spectrum of a light water reactor compared to the neutron spectrum if you have it for a liquid sodium cooled reactor. And you can see that the neutron spectrum is much faster in the sodium cooled reactor. So that, and in fact, I mean, Szilard did all this in one paper in the spring of 1945, and But in fact, that's a path that worldwide that the nuclear engineering community pursued, and in some parts of the world are still pursuing, ever since. So, in fact, the industrialized countries started racing to commercialize this idea. And I've got 7 listed here on this slide. 4 who eventually quit, 4 countries that eventually quit, and 3 which are still at it. The United States, the last sodium-cooled reactor that it built was actually built by a commercial consortium outside of Detroit, and it was fairly small, but that was the size reactors they were building at the time. I'll explain to you why the countries quit, but just briefly, you can see then UK, France, and Japan all built a series of reactors, ending up with a demonstration prototype, where the largest was France's, which is a really full size by modern standards, 1,200 megawatt reactors, the Super Phoenix. And then those that are still going are Russia, which has had about I guess it started about 10 years after the US breeder program, but then they've kept at it. And their most recent sodium-cooled breeder reactor is the VN800, about 800 megawatts, and which came online in 2015. India has built a reactor, 500 megawatt reactor, that has been delayed from year to year by various technical problems coming online, but is basically being debugged at the moment. China is building 1, maybe 2, 600 megawatt reactors that are you can see them on Google Earth. China's moving pretty fast. Now, the problem with the sodium-cooled reactors is sodium. Sodium burns in air or water, and so you really have to go to great lengths to make sure that it doesn't come in contact with air or water, which makes refueling complicated, makes repairs complicated. Actually, Admiral Rickover, who led the development of light water reactors, PWRs, pressurized water reactors for U.S. submarines, was attracted to the sodium-cooled reactor because it can be more compact than a water-cooled reactor. But he actually put one on the second U.S. Nuclear submarine, the Seawolf. But he pulled it off very quickly after it had suffered sodium leaks, and his conclusion is that it's expensive to build, complex to operate, susceptible to prolonged shutdown as a result of even minor malfunctions, and difficult and time-consuming to repair, has really been has been borne out by the experience of most countries with breeders. Here I show in this table, I guess 10 prototypes that have been online, and show their by capacity factor. The capacity factor, for those of you who are unfamiliar with it, is just the percentage of electricity that a nuclear reactor produces compared to what it would produce if it were operating 100% of the time. And for reference, worldwide, the average for light water power reactors, the dominant reactor type, we have is about 80%. In the US, it runs more like 90%. So the Russia has had pretty good success, although with the predecessor to the new prototype, which is both are operating, it did have 14 sodium fires in the first 15 years before it got into a relatively trouble-free regime. Japan at the bottom of the list had one sodium fire, and that basically did them in. They never were able to get their prototype up again. So, and then the rest of the world was in between, and this I think explains, in the case of the except for China, why countries dropped out. That's one reason countries dropped out. Now, it became a public policy issue beyond the energy policy because of the nuclear weapons connection. The U.S. Atomic Energy Commission really, especially under the leadership of Glenn Seaborg, promoted the breeder reactor as the reactor of the future. Actually, Seaborg even talked about the world going to a plutonium economy, where plutonium became the measure of value, replacing gold. So Seaborg and the Atomic Energy Commission under Seaborg was the longest the longest duration chair of the U.S. Atomic Energy Commission for a decade. Seaborg had actually shared a Nobel Prize for being a co-discoverer of plutonium. He had also, as a nuclear chemist, he developed the first reprocessing technology. Reprocessing is the chemical separation of plutonium from all the fission products and uranium in irradiated uranium. And so he definitely knew that plutonium is a nuclear weapons material, but he ignored that fact in promoting plutonium as the fuel of the future. And 4 years after he stepped down, India, which is one of the countries that the U.S. Atomic Energy Commission was helping to develop a breeder program, used some of the plutonium that we helped them separate for a nuclear, what it called was a peaceful nuclear explosion. And in fact, that seems strange today, but in fact, in those days, the US nuclear weapons labs were promoting peaceful nuclear explosions for all sorts of things, including building canals, actually even for fracking, shale to free up natural gas. So, so after India's nuclear test, the breeder reactor program was no longer left to the Atomic Energy Commission. The White House became involved and to try to figure out the costs and benefits of this effort. The Ford administration, which was in office at the time, discovered that 4 other countries, all under military rule at the time, were on the verge of were completing deals to buy reprocessing plants from Germany and from France. The Ford administration reversed U.S. policy of promoting reprocessing abroad and brought a lot of pressure on France and Germany to not deliver on these deals. And in fact, the Pakistan got most of the most of the design from France before France terminated its deal, and ultimately did build that reprocessing plant. But it was after Pakistan had gotten nuclear weapons by another route, which is uranium enrichment. Now the Carter administration came in and looked at whether the U.S. should continue a domestic breeder reactor program, and the two questions were: is it economic, and is it necessary? And they concluded, and I was involved in this review, and they concluded that the answer to both questions were no. And then there was a struggle over both the U.S. breeder program and reprocessing. At the time, there was an agreement with the utilities, an AEC agreement with the consortium of utilities to build the construction of a demonstration breeder reactor in Oak Ridge, Tennessee, the so-called Clinch River breeder reactor. That was of interest to Howard Baker, Senator Howard Baker of Tennessee, who was the leader of the Senate Republicans, and when they became the majority, he became the majority leader. So despite the Carter administration, this project outlasted the Carter administration. And also at the time, there was a large reprocessing plant under construction next to another AEC site, the Savannah River site in South Carolina, where in fact a good portion of the US weapons plutonium had been produced. And so going back to the breeder though, during those years and into the Reagan administration basically did not think what the US did at home would necessarily have an effect on what other countries did. But the cost of those of you who've been involved with DOE will be familiar with, DOE is of course the successor to the AEC and has had a lot of problems with cost control on big projects. And that's what happened here. The original cost estimate for the Clinch River breeder was 0.7 billion with the 50-50 cost sharing between the AEC and the consortium of utilities. But the utilities stressed, made sure in the agreement that any cost overruns would have to be covered by the government. And so as a result of cost growth, it became like a 90-10 instead of a 50-50 agreement. And at that point, the Congress pulled the plug. At the same time, with regard to reprocessing, the reprocessing plant, the Reagan administration said, if the utilities want to build this reprocessing plant and use it, that's fine. But the government isn't going to pay for it, and that killed the reprocessing plant. And instead, the utilities came back with a proposal that the government would build a geological repository for their spent fuel, and that they would pay a mil per kilowatt hour, a tenth of a cent per kilowatt hour, to pay for their share of that repository. Of course, that's became the Yucca Mountain repository, which then got stuck due to the political opposition in Nevada. So other things changed. The expectations which required the breeder reactor turned out to be wrong. And here I show you the growth instead of the trajectory. This is global nuclear capacity. This is a projection made by the IAEA in 1975. Instead of there being an exponential growth of global nuclear capacity, the global nuclear capacity plateaued. So the demand for uranium didn't go up as high as had been assumed. And in the same projection, they assumed that breeders would start being commercialized on a large scale in 1990, and that we'd have 200 gigawatts of worldwide of breeder capacity by the year 2000, which was the end of their projection. The other thing, and here I explain what one factor in that in the lower growth of not just nuclear power, but of all power. It turned out that 1970 was a transition year between a high growth for electricity in the United States and worldwide, where the U.S. Electricity production was doubling approximately every decade, to a period of much lower growth, which is growth comparable to the growth rate of the economy. The high growth in that first 50 years I show here before 1970 was due to economies of scale in electricity production. In fact, the share of the GDP, the gross domestic product, that was going to the purchase of electricity during those 50 years did not increase because electricity kept getting cheaper. But that stopped in around 1970, and so we had this slower growth, and so we went from a 27-fold increase in electricity production in that first 50 years to about a 2.6-fold increase in the next 45 years. And in fact, if the U.S. growth had continued at that pre-1970 rate, we would be consuming more electricity than the world is today. Today, the U.S. and for a long time, the U.S. Nuclear power production has been about 20% of the U.S. total electrical power production. Globally, it's about 10%. So I'm keeping track of I want to keep this, get to the end in about 10 minutes. So the other thing, Szilard was wrong and his colleagues were wrong about uranium being scarce. This shows a geologist's estimate in 1980 when this issue was being debated about the abundance of uranium as a function of the ore grade. And it shows that in the 1980s, we were using ore about 0.1% uranium. And by the way, the peak here is at about the 3 parts per million. That's the average crustal rock. And since that time, we've actually moved. We started to mine the next bar. And in fact, about 40% of the world's uranium in 2018 came from Kazakhstan, in situ leaching. They basically pump acid underground into sandstone, which contains uranium, and then the uranium comes up in solution, and then they strip out the uranium and send the solution down again. So that it turns out that there's plenty of uranium, and in fact, I'm sorry, this arrow here on oceans moved. I forgot to move it, but basically to the right of the gap, it shows you uranium in ocean water, and which is much more dilute than the uranium in the crust. But in fact, people have been looking at whether it might be possible to put things in the ocean with fabrics impregnated with chemicals that pick up uranium, and they have concluded that we're within an order of magnitude of in terms of cost of being able to do that. So that's what happened to the breeder reactor, and here you can see it played out in economics. The cost of uranium has not been going up. If you can see a trend here, maybe it's slightly downward. And it has had peaks at times when utilities thought that there were going to be a lot of nuclear power plants built, and that the mining industry wasn't going to be able to keep up, and therefore they started building up stockpiles of uranium. But the price is low. Today it's about half of that, the central value in my graph, the $100 a kilogram, and even at $100 a kilogram, the cost of uranium, the contribution of the cost of uranium to the cost of generating nuclear power from a light water reactor is about 0.3 cents. It's about 3% of the cost of nuclear power from a new nuclear power plant. Most of the cost is associated with the capital. There's actually a fair amount of cost associated with the fact that you have about 1,000 people working at a gigawatt nuclear power plant. And just in case, mostly, I mean, there's guards and people there just in case, and that costs a fair amount of money as well. Now, but in some countries, civilian had started separating plutonium to provide the startup cores for the breeder reactors that they expected that they would be building. And here on the left side, left plot, I show the total amount of plutonium, separated plutonium in the world, divided into two categories. One is weapons plutonium, which was dominant during the Cold War. That's the two brighter shades of red. And then with the brightest shade of red, you can see that in fact, the amount of plutonium in warheads plummeted after the end of the Cold War, because the US and Russia went down from about 65,000 warheads to about 10,000 warheads, or 9,000, 10,000, including all the other countries. So all of a sudden we have most of that Cold War plutonium as excess. But in addition, the civilian plutonium, has continued, which was in programs that were originally launched to provide plutonium for these starting up these breeder reactors. Civilian plutonium has continued to increase, and it's dominantly in four countries. The UK has the largest stock, and it's finally stopping reprocessing. Its breeder programs ended in 1994. It's finally stopping. Then there's Russia, which has, as I mentioned, still has a breeder program, but it actually hasn't used fuel to, hasn't used plutonium to fuel them until very recently. And so its stock was growing all this period. And then we have France and Japan, which abandoned their breeder programs, but continued to reprocess. And what they're doing to control their stockpiles, France is doing it successfully, relatively successfully. Japan, not so much. They basically are producing fuel, so-called mixed oxide fuel, plutonium, maybe around 8% plutonium mixed in with depleted uranium as a substitute for low enriched uranium. But France, which as I said, its program is working relatively well, is only saving about 10% of the low enriched uranium it otherwise would have used in this way, and at 10 times the cost of the low enriched uranium. So it is a mystery, and I'm in the middle of writing something about trying to understand why these programs continue. I call them zombie programs. And sort of my tentative conclusions, I'm still wrestling with this and debating with colleagues, is that that they and I'm conscious of that I want to end this pretty quickly so we have time for discussion. These programs are driven by powerful organizations and that don't want to admit they were wrong. In China, India, and Russia, with the breeder programs, they're R&D programs, and as you know, in R&D, there's a fair amount of latitude given to the people who are running these programs, and we have zombie programs in other areas. Like I think I would consider the space station a zombie program. In France, I think that there are other factors that come in. There's lots of jobs, 6,000 jobs associated with its reprocessing plant. It's a huge plant. And France is also trying to sell reprocessing plants to other countries. It's been, since 2007, it's been talking with China. The China National Nuclear Corporation wants to buy. I think China likes to acquire technology. And in Japan, there's a number of factors, including Japan's the only non-weapon state, including the fact that Japan, which has a large stockpile of plutonium, can say to the US, if we lose confidence in your nuclear umbrella, we can always get our own. And that certainly is a way to get attention in those discussions. Let me just skip over South Korea. And there's, so why have I spent so much effort on this issue? Well, there has been a concern about nuclear terrorism. During the 1970s, there's a former Los Alamos nuclear weapons designer argued publicly and with a considerable impact that it was you no longer required a bunch of Nobel Prize winners on a mesa in New Mexico to build a plutonium bomb, that it could be done by ordinary people now, and the terrorists might be able to do it. And there's also the fact that plutonium oxide is very carcinogenic. And so if you're worried about dirty bombs, you have to worry about plutonium as well. There's proliferation. There's been a long debate about whether reactor-grade plutonium can be used to make a bomb. I can go through that if you're interested in the discussion. There's some concern, I have concern, that the Indian and Chinese programs may be dual purpose. Both those countries have a small amount of weapons-grade plutonium. A breeder reactor produces plutonium, weapons-grade plutonium. That's plutonium, which is almost pure plutonium-239. It produces that naturally in its blanket. And here I show a wedge out of the core designed for the Indian breeder. You see the black hexagons there are depleted uranium, and some neutrons come out and make some of that U-238 into plutonium.
Hey, Frank, we've got a question.
Yeah.
Yeah, so Paul asks, what's your opinion about burner fast reactors to transmute long-lived actinides to short-lived fission products?
Yeah, I should advertise a book that I've written. I don't know whether, am I on camera now, or is my slides still on camera?
Yeah, you're visible too.
Okay, so anyway, I co-authored a book called Plutonium, how nuclear power's dream fuel became a nightmare. I don't know whether you can see it, but it just came out. And there's a chapter in there on the issue of the hazards of burying spent fuel in a deep repository. And this is actually, there was a more authoritative, one of my authorities, there was a major study done on this by the National Academy of Sciences, whether it was worth separating out plutonium and other transuranics, long-lived transuranics, to decrease the hazard from very spent fuel. And usually this hazard is presented as, what if you went down and ate this material? Then the plutonium and transuranics would dominate the toxicity. But if you Sweden's repository company has done simulations. What if their repository failed? And plutonium and the other transuranics are relatively insoluble in the oxygen depleted deep water. And so when they modeled, what came up and what dominated the dose to a farmer, above, with this drinking and eating food grown with this contaminated water coming up through the cracks in the granite, they found that in fact the transuranics did not dominate. In the short term, there was carbon-14. Then which is I didn't realize was in spent fuel, but there's some nitrogen there that gets turned into carbon-14. And then iodine-129, which is a long-lived fission product, very soluble. And then finally, in the million-year region, radium, which we're familiar with because of its decay product radon, which accounts for a lot of our natural radiation dose. So based on that study and the similar conclusions by the Academy of Science, I think the public's concern about which is stop the Yucca Mountain, about buried radioactive waste is really grossly exaggerated. For me, my hierarchy of concerns is on the top the nuclear weapons connection, in the middle reactor safety, and then way down in the bottom, the buried spent fuel. And it's interesting that in Sweden and Finland, where they have been able to site repositories, they're adjacent to nuclear power plants. And those communities know that they would rather have the spent fuel deep underground than forever on the surface. So, you know, I don't know whether it would work that way in this country or not, but that's sort of my maybe a too long answer to your question. So I'm basically, what I'm saying is that the hazard from a repository, in my view, is similar to the hazard from a deep uranium deposit. So I don't know, I don't see any other questions here in the group chat. So I basically was finished, or shall we go into our discussion?
Sure. I think you had one more concluding slide, but that's your call. There's
okay. Well, I'll just
now we can't.
Yeah, just this is one that's still under development. You know, about what can you do if you agree with me that it's a problem that these plutonium separation programs are continuing, and I just had a list of ideas. I gave this talk yesterday, and a lot of people disagreed with me about it. So I'm not pushing them today. but if you like, I could go through them.
That's up to you. If you'd like to just go ahead and open up the floor for questions.
Yeah, let's open it up, and
yeah, maybe looking at
and people can see it on their screens if they're interested.
Yeah, this might prompt some. So everyone, if you have a question for Frank, because there are about 35 of us, 38 of us on the line, rather than speaking out, if you don't mind posting it to the chat, Frank can see your question if you post it to him or to everyone, and he can respond.
There's a stunned silence.
Okay, well then here we go. Oh, wow. We got like 5 at a time.
Okay, things are starting to come in now. Fast reactors, not for breeding. Well, I mean, the fast reactors do have a economic problem, and even in Russia, which has been the most successful with fast reactors, Rosatom, which is a government-owned company, but is supposed to make money. The people who built the BN 800, which came online in 2015, expected to go on to build a BN 1200. These numbers are the rough ratings in terms of generating capacity in megawatts. And Rosatom's said, well, it doesn't look like your design would be economically competitive with our water-cooled reactors. Why don't we put that off for a decade? And you know, we can build it in the 2030s if you come up with a good design. So that's the problem. You know, I mean, the original mission of breeders was to generate electricity. There's been some promotion of fast reactors to do what John mentioned, fishing to actually burn plutonium and transuranics instead of breeding it, to get so that it doesn't get buried. But that's been pretty much rejected, even in France, and as a adequate rationale. So the question is, what other reasons? I mean, you know, beyond the prototypes or experimental reactors would make sense, and that's why I suggested that the model fusion is a similar problem with the magnetic fusion, and they're so far away from commercialization that they actually joined forces to build an international fusion reactor in southern France to sort of advance the state of the art. See, and one of my proposals on this last slide is that maybe this is the way the breeder community should go if it wants to. Maybe instead of, I mean, there's no reason to compete right now because we're not yet at a commercialization stage. So maybe a joint project like the fusion people have, or like the space station, would make more sense. I guess I should give shorter answers. Thorium fuel cycle. That was another way to have a. You can actually, with a thorium fuel cycle, you can actually have a breeder reactor. And in Oak Ridge was developing a molten salt thorium reactor, and the Canadians showed that they could actually have a self-sustaining system, you know, which with thorium. Thorium U-233 cycle instead of a uranium plutonium cycle. It's again reprocessing is costly, and the question, and I think the Canadians concluded and that you know that the once-through fuel cycle that they have with their heavy water reactors really is more economical. The Indians have been thinking about a thorium cycle. They have heavy water reactors. So one of the arguments for it has been that thorium is further down the periodic table, and therefore you wouldn't have as much plutonium in the spent fuel and other transuranics. But as you've seen, I haven't given that argument much weight. Lead-cooled reactors. There's been interest in lead-cooled reactors as an alternative to sodium-cooled reactors. In fact, Russia is building one of those as well, a 300 megawatt reactor in one of its nuclear cities. There actually was a the Russians actually did build lead bismuth. It's a lead bismuth alloy which has a low melting temperature. They actually built I think 9 submarines. It went further down that track than Rickover did. With those reactors. They were very fast submarines. So they have some experience with that. They had a couple of accidents in those 9 submarines. So it was a mixed experience, and they abandoned that. But it is lead is less reactive with air and water, and it apparently is quite corrosive. So that's a problem that has to be dealt with. Accelerator with a you know, there have been proposals to have a subcritical reactor driven by an external accelerator. As I think the argument has been that maybe keeping reactors subcritical would be have safety advantages, but I haven't gotten into that very much. It was the accelerator people at the in Europe's the Geneva-based CERN were promoting that for a while, but I haven't heard much. I think the Belgians may be building something along those lines, but I don't know much about it. I haven't gotten into it. The Secretary of Nuclear Energy is supportive of fuel reprocessing. I think if I had discussions with her, I know that the Office of Nuclear Energy I think that's what you're. This is Paul who wrote this question. I think what you're referring to is the woman who runs the Office of Nuclear Energy in DOE, and she's from the Idaho National Laboratory, and Idaho is where we built the experimental breeder reactor number 2, which was a very interesting reactor, and they very much devoted to it still. I actually was involved in shutting down the experimental breeder reactor number 2 when I was in the Clinton administration, and they have managed to convince the Office of Nuclear Energy and a fair number of people in Congress that we should embark on building a bigger version of EBR2. I think 300 megawatts thermal as what they call a versatile test reactor. If in fact fast neutron reactors are commercialized, and there are various proposals, then we would need, the argument is that we would need a source of fast neutrons to test materials and fuels. I'm a skeptic myself. I don't see these proposals for commercializing fast reactors going very far based on the history. But there is, you're right, there is interest right now within the Department of Energy. The cost of that versatile test reactor is estimated at $3 to $6 billion, and the price again it keeps going up. So I think it may in the end, like the Clinch River reactor, collapse under its own weight. And I think I got. Oh no, I didn't get to the end of it. There's another one.
Yeah, this probably needs to be the last one, Frank. We're
okay.
We're against 5 o'clock.
Okay, thanks. Will the current economic and humanitarian crisis affect the nuclear industry? I'm not really a pundit on this. I'm not sure that it will in the long term affect the nuclear industry that much. But other people who understand the economy better than I may have a deeper answer. Okay, well, thank you, all of you for tuning in. And
yeah, thanks everyone also for the questions to Frank, but more importantly, I want to thank Frank for taking the time to meet with us today, and we don't all have to applaud, but thank you very much, Frank.
Thank you, and enjoy the rest of your day. And I'm happy if anybody wants to continue this discussion, for you to share my email.
Okay, I'll do that. I'll make sure to post it when the announcement of the video comes out, okay?
Okay, thank you.
Thanks a lot.
Take
Bye.
care. Bye.